Hi students, welcome to preliminary chemistry and the energy topic. This is video number 11 on combustion reactions. When hydrocarbons burn in the presence of oxygen, they form, generally speaking, carbon dioxide and water. This assumes an excess of oxygen, and we'll see as we go through this that the amount of oxygen can actually affect the product. Combustion reactions are exothermic as they generate a lot of heat energy. One example of these would be butane, C4H10, in the presence of oxygen, and we'll call it a liquid coming out of the cigarette lighter, and it's going to form carbon dioxide and water. Of course, we need to balance that equation. In order to do that, we're going to have an odd number, so I'm going to have to double that. So 10 here, 2 furthers 8 there, and excuse me, 8, 16, 26, 13 there. Combustion may still occur in low oxygen environments. However, the products can change. One of the things that we know about that happens when hydrocarbons burn is that if as the oxygen levels decrease, we always have water formed as one of our products, but the other product changes. Carbon dioxide if there's a large amount of oxygen available, carbon monoxide if the oxygen is reduced, and even carbon in the form of soot if the oxygen levels are quite low. We can demonstrate this simply by looking at the Bunsen burner. Now, of course, in the Bunsen burner, we're more likely to be burning methane, CH4, plus O2, and that's going to form CO2 plus H2O. Now, the assumption here is that we have 2 to 4. The assumption that we have here is that we have the hole fully opened, so we have a high oxygen environment. So these are gases and a liquid, and these are what you get when the oxygen levels here are high. When the hole is closed in the Bunsen burner, of course, the oxygen concentration is very low. There's no oxygen that can get into the base of the tube, only the oxygen that can sort of get in around the top. So the burning is very low, and you'll often find when we use this flame that we leave a black mark on what we're heating, because test tubes, those sorts of things. That black mark is carbon. So we still get our water forming, but carbon as a solid actually forms as a consequence of what happens when the oxygen concentration is very low. 2 here, and that's it. When the hole is partly open, then we have a little bit more oxygen available. Whoops, that's not a solid, that's a gas. And oxygen. And so this time we form carbon monoxide gas and water. Now I think it's going to be an odd number, so I'm going to have to double to 2, 2, 4 there. So I have now 4 and 2 is 6 and 3. So you can see the ratio is changing as we go through each of these. So if we talk about the fuel to oxygen mix, at low O2, we have a 1:1 ratio. So this is low O2 here, low. At moderate, we have a moderate O2. We have a 2 to 3, which is the same as 1 to 1.5. And then at high O2, our fuel to oxygen mix is 1 to 2. And we get that just by those coefficients in front of those substances. So you can see here that we do have some significant consequences if the fuel to oxygen mix is close to 1 to 1. That means the oxygen levels are very low. If they're closer to 1 to 2, then the oxygen levels are very high. And that's actually changing our product, or at least one of our products, in each of these reactions. Now, I talked in previous videos about what is being marketed as clean coal. Coal effectively is used for power stations in the form of coke. So the volatiles have been removed. Obviously, they need to be removed in the absence of oxygen, or you're going to end up combusting everything. But when this coke is heated in oxygen, the fuel produces 394 kilojoules per mole. And that's effectively an equation that just comes out as carbon and oxygen producing carbon dioxide. If the oxygen levels are reduced, then we can drop from carbon dioxide to carbon monoxide as a product, and we also reduce the amount of energy. And you'll have noticed this with the Bunsen burners as well. When the oxygen levels are lower, the flame is not as hot. That orange flame is not as hot as the blue flame, which is what you get on higher oxygen levels. And the same thing is true when we burn coal. Petrol also is something that's commonly combusted. It's very volatile, and a lot of the hydrocarbons that are used for combustion are low molecular weights. Even petrol is usually an octane, so a carbon 8. And they readily vaporize, and as we know, they combust when they are sparked. The products, again, depend on the air-to-fuel ratio. Remember, I looked at that in one of the previous slides. And modern fuel injection systems are electronically controlled to ensure the optimum mix for maximum power and minimum pollution. So we want high energy output. We want low pollution. And catalytic converters have also been fitted to a lot of modern cars in order to reduce the carbon monoxide emissions. The carbon monoxide is converted into carbon dioxide before it leaves the car's exhaust. Often that happens in concert with any nitrous oxides that are produced in the pistons as a result of combustion reactions. The nitrous oxides are quite dangerous in the environment, and the interaction between those and carbon monoxide can turn those nitrous oxides and the carbon monoxide back into nitrogen gas and carbon dioxide. Not great, but better than the alternative. And finally, combustion of crude oil fractions. Well, we know that for octane, we get 5,470 kilojoules per mole for complete combustion. So this is CO2 as a product, and high oxygen. Only just over half of that if we have incomplete combustion. So different products and also lower oxygen. The heavier hydrocarbon fractions require a wick to increase the surface area of the fuel-air mixture for combustion. So candles do that. They tend to be more solid at room temperature rather than liquid, and therefore we need to spread their surface area out in order to combust them. Thanks for watching.